To predict catastrophic flooding, we have to know how much water is falling from the sky. Look at the water level against this submerged structure. When rivers overtop their banks, thousands of lives depend on accurate early warning models. We hold back these millions of gallons using massive concrete structures, but the safety and operation of that heavy infrastructure relies entirely on tracking a microscopic input: individual drops of rain. The problem is that precipitation doesn't fall in a uniform, predictable sheet. It is a chaotic mix of interacting physical variables colliding in real time. To make sense of this chaos, hydrologists filter weather data through a three-part analytical matrix. They track the lifting mechanism, the physical form it takes, and the engineered ground capture. If we fail to control for these variables the exact moment the water hits the dirt, our data is corrupted. And with bad data, our entire hydrological prediction model collapses. The water cycle starts miles above us with three primary lifting mechanisms. The first is convective lifting, where the ground heats up and creates aggressive vertical updrafts to build local storm systems. The second is orographic lifting. When moving air hits massive topographic barriers like mountain ridges, the wind is forced aggressively upward, condensing into heavy cloud layers. Finally, we have cyclonic or frontal lifting. This happens when contrasting pressure zones and varying air masses violently collide, forming massive spiraling storm systems over the ocean. While these massive atmospheric engines operate miles above our heads, they physically dictate the exact microscale geometry of the individual drops that eventually fall back to the surface. This chart maps the relationship between lifting mechanisms and physical forms of precipitation. At the smallest end is drizzle, floating droplets under 0.5 millimeter. Contrast that with standard rain, with heavier droplets ranging up to 6 millimeters. This difference in mass creates a serious aerodynamic complication. A heavy 6 millimeter drop has the terminal velocity to push straight down through a crosswind, but a tiny 0.5 millimeter drizzle droplet is highly vulnerable to being blown sharply off course by that exact same wind. Because every storm produces a wildly different combination of drop sizes, the aerodynamic behavior of the water right before it hits the ground is highly unstable. To measure this chaotic variable, hydrologists rely on tools like the Simon's non-recording rain gauge. As you can see in the schematic, it uses a precise 127 millimeter diameter rim collector to funnel the water down into a measuring jar. But that precision is entirely compromised if you place the gauge anywhere near a solid vertical obstacle, like a tree or a tall building. When uniform wind crashes into a vertical wall, it creates a wind shadow. The air splinters into chaotic, swirling updrafts on the leeward side. If your rain gauge sits in this turbulent zone, the updrafts directly exploit the low terminal velocity of light drizzle. Instead of falling neatly into the gauge, those lighter droplets are physically blown over and away from the 127 millimeter funnel. The storm happened, but your instrument missed it, rendering the entire dataset useless. To eliminate wind shadow variable entirely, hydrologists established a strict mathematical sighting requirement in these engineering class notes. The rule dictates the gauge must set at a distance equal to twice the height of the nearest object, or a minimum of 30 meters away. When implemented correctly, it looks like this. You have an expansive, perfectly flat clearance completely separating the gauge from the nearest tree line. By locking in this unobstructed radius, hydrologists solve the third and final column of our matrix. This strict 2H clearance creates a functional aerodynamic buffer, an invisible engineering structure that isolates the water cycle's truth from the chaos of the wind.